So, can a machine predict your future salary? That's not a hypothetical question. That's exactly what we are going to show you today. If I told you that two variables, a few data points, and one mathematical concept is all that you require to make precise predictions about salaries, fuel efficiency, and almost anything else that follows, would you believe me? Maybe not. But by the end of the video and the presentation, you will. So, hi everyone, my name is Vishesh, and alongside our team today, we are going to take you through the mathematics of prediction. We start off with the tool that makes it all possible, partial differentiation. And then we'll show you how it connects to linear regression, and then we'll supply it to two completely real data sets and predict outcomes that weren't even in our data.
So, we have just gone through the roadmap of what we are going to cover today. I'm Riola and I'll be walking you through the mathematical idea that holds all this together, which is partial differentiation. Now, most of us already know what differentiation is, right? So, you take a function, you calculate how it changes, and that gives you a rate of change. It's pretty straightforward. But in real life, things are rarely dependent on just one variable. So now think about something like predicting house prices. It's not just one factor. It depends on size, age, location, and more. So instead of like a simple function, we deal with something like f of xy, multiple inputs but one output. And that's completely what changes how we differentiate. So that's where this symbol comes in, which is dou called partial. And you're going to see it again and again throughout this topic. So the next question is, why can't we use normal differentiation here? Let me break that down for you. So like over here, you can see on the left, we have a function f of x 3x squared plus 2. Just one variable, one direction of change, one clean derivative. Everything is straightforward. Now let's compare that with this function at the bottom. F of xy 3x squared plus 2y plus y squared. Now we have got two variables. But now if you try to differentiate both at the same time, we lose clarity about what actually is causing the change. So it's like trying to figure out whether the house prices increased because of size or because of age. If both change together, you can't separate the effect. Now, look at the 3D surface on the right. That curved shape represents a function with two variables in space. At any point on that surface, you can move in two directions. The pink arrow dou f by dou x means that we are keeping y constant and only changing x. The white arrow dou f by dou y means that we fix x and only change y. And that log symbol is very intentional because it shows that we are freezing one variable so that we can study the other one clearly. So that's the whole idea. Change one variable and keep other everything else fixed. Now that we understand partial differentiations individually, let's see what happens when we combine them. Now let's take this function f of xy, x squared plus 3xy plus y squared. First, we differentiate it with respect to x, treating y as constant. So that gives us dou f by dou x equal to 2x plus 3y. Now we differentiate it with respect to y, treating x as constant, and we get dou f by dou y equal to 3x plus 2y. Now we put both of these together in a vector form, and now this is called the gradient, written as del f. So we get del f equal to 2x plus 3y, comma 3x plus 2y. And this is the important part. This gradient vector always points in the direction of the steepest increase. In other words, the fastest uphill. So if we move in the opposite direction, which is like the negative gradient, we go downhill towards the lowest point. And that lowest point is exactly what we want in things like linear regression, which is the minimum error point. And that's exactly what Saugandhika is going to show you next.
Thank you, Riola. So Riola just showed us the mathematical tool, partial differentiation. Now, I'm going to show you exactly where we use it and why it matters. Let me ask you one thing before I put anything on the screen. If a person has 6 years of work experience, what do you think their salary would be? Just think about it for a second. Don't answer yet. Now, let's say a company collected data on their employees, years of experience on the x-axis and salary in 80,000 on the y-axis. Let's see what they found. 1 year of experience, 3,000. 2 years of experience, 4,000. 3 years, 5,000. 4 years, 6,000. Now you're starting to see something, aren't you? 7, 9, 10 years. The pattern is clear. As experience goes up, salary goes up. This is what we call a positive linear relationship. But if a new employee joins, let's say within 7 years, not in our data, what do we do then? We need a line. But which line? Infinite lines could pass through this data. This one. Mathematics has chosen it. Not intuition, but maths. That's next. How does math decide which line is the best? It measures how wrong each line is using the cost function. These vertical lines are residuals, and as you see, the gap between them, what the line predicted, and the actual salary. Some long, some short. Everyone is a mistake. Switch to the best fit line. The arrows shrink dramatically. That's what we're minimizing. Total error across every point. But we can't just add the arrows. Some points sit above the line, as you can see, some below. They cancel each other and give us 0, which is misleading. So what we do is we square each error, making everything positive, then average them. That's the mean square error, J of M and B. Yi is the actual salary, Mi plus B is our prediction. Square the difference, average across n points. J tells us exactly how wrong our line is. Bigger the J, worse line. Smaller j is the better line. Now, the crucial insight. J depends on two unknowns, M and B. That makes it a multivariable function, exactly like Riola's f of x and y. And to minimize a multivariable function, we use partial derivatives. J is a function of M and B. To minimize it, we take partial derivative with respect to each variable set to 0. What we do is, first, how does the error change as slope changes? We differentiate with respect to M, freeze B, okay, and set it to 0. Simplifying gives us the normal equation 1. Some process for the intercept, freeze M, differentiate with respect to B, set to 0, normal equation 2. Now, two partial derivatives, two equations, two unknowns. Solving them simultaneously gives us the exact M and B that minimize total error. This is gradient descent, expressed analytically. Instead of iterating down the bowl step by step, we jump straight to the bottom using calculus. Solving these equations gives us our final formula. For slope m, the numerator is n sum of xy minus sum of x sum of y. This captures how x and y move together. Denominator is sum of x squared minus sum of x squared. How much x varies on its own? The slope is simply the ratio of those two things. Now, for every 1 unit increases in x, how much does y change? That's m. Top, how x and y move together. And bottom, how x varies alone. Elegant once you see it, right? Once we have m, b is straightforward. Sum of y minus sum of n into x divided by n. It takes the average y and subtracts the slope's contribution. What's left is the baseline. So we calculate m first, b depends on it. That order never changes. Some formulate two completely different data sets, two completely different stories. That's the beauty of what we built today. Partial differentiation isn't just an abstract mathematical technique. It's the reason a regression line lands exactly where it should and not anywhere else. It's mathematics behind every prediction, every model, every data driven decision. Riola introduced the tool. I've shown where and why we use it. Now watch it come to life with real numbers.
Thank you, Sagantika, for that great explanation. So this is the case one, which is experience versus salary, in which there are 7 employees. The main one question that we have is what's the relationship between the data of the 7 employees? On the left, you can see a table of experience in years and salary in AED thousands. The first is 1 year of experience, which is having 3,000 AED salary, and then two, which has 4,000, 3, and 5,000, and so on. In the center, you can see a graph on which this is plotted. On the y-axis is the salary in AED thousands, and on the x-axis is the experience in years. So the first plot is 1, comma 3, 1 on the x-axis and 3 on the y-axis. Then the second one is 2, 4, and accordingly. So what you see over here is a positive relationship, which is a linear regression. As experience rises, salary rises. The data already tells us the direction. Now let's use the math to tell us exactly how much. All right. So the next thing is finding M and B. On the left, you can see a table in which X, Y, and then the new thing, which is X squared and XY has been written. So on the bottom of the table, we calculate the summation of X, which is 37. Summation of y is 51. Summation of x squared is 269. Summation of xy is 343. We need summation of all of these values for calculating m and b. So the first step is finding the slope m. The formula that Sugandhika showed is what we are going to use here. M is equal to n summation xy minus summation x summation y, the whole divided by n summation x squared minus summation of x the whole square. So we just need to put the values from the table that we have into the formula. After putting the values, so we get the final answer as m is equal to 1. That means that the slope is 1. This indicates that the salary increases by 1000 AED per every year of experience. So the slope of the graph represents represents the increase in the salary, and as m is 1, the increase in salary in 80,000 is 1000 per year. So the second step is finding B. So finding the intercept B using the formula that's been showed before. B is equal to summation of y minus m summation of x, the whole divided by n. So putting the values from the table back into the formula, we get B is equal to 2, which indicates that the base salary of 2000 AED with 0 years of experience. If there's 0 years of experience, then the base salary will be 2000 AED. That has been calculated using the formulas. All right, so this is the results and prediction. On the left, you can see the graph on which the plots are shown, and the line y is equal to x plus 2 is the linear regression equation that we have over here. For the model performance, it is r square is 1.0, indicating that the model explains 100% of variation in salary. R square is 1.0, which means that there's no error in explaining the variation in salary. And every single point comes on the line y is equal to x plus 2. So predicting for 6 years experience using regression. So if we want to say 6 years was not given on the table. So if we just put y is equal to x plus 2 and x is the years of experience, which is 6, we'll get the predicted salary as 8000 AD, which is not given in the table. So the linear regression equation is y is x plus 2 having 100% accuracy. So the limitations of this is there are only 7 data points. It is a small sample. If there would have been a huge sample, then the accuracy of prediction would have been a lot better and being more precise. Real salaries depend on more than experience alone. Real salaries in the real world don't just depend on experience, it also depends on location, it also depends on education, it depends on a lot of factors, which when considered will give a more accurate result, which is one of the limitations in this model. R square is 1 is rare in real world data. So this is the C++ code for verifying the results. I'll just explain the code and the short output that we have over here. Everything that the calculation of the slope and the intercept is done in this code. So we have the main in which there are two arrays over here in which the values have been put from the x and y columns 1, 2, 3, 5, 7, 9, 10, and 3, 4, 7, and so on. The n, the number of elements over here is 7. So we initialize some values to 0. And after that, we run a for loop to calculate the individual sum. You would remember that there was a summation of x, y, xy, and x squared. So that is done using the for loop and the sum statements. So the formula that Saugandhika demonstrated that showed the final calculations is being put over here in the double M. M is equal to n times summation xy minus sum of x into sum y. And that's the formula which has been put in the C++ code. And then the linear regression equation has been printed accordingly according to the slope and the intercept. Then comes the prediction for year 6, which is the final thing that's been calculated, which is according to the linear regression equation. So the output for this code is y is 1x plus 2, which is a linear regression equation. And the prediction for 6 years of experience is 8, which indicates 8000 AD in salary.
Same idea, but opposite story. Thanks, Prithvi. We just saw the line going up. Keep this in your mind because my graph does the opposite thing. A quick question. When a car gets heavier, does the mileage get better or worse? Naturally, a heavy car needs a more energy, so most of you probably guess the worst. Let's look at the data. Here are seven cars. Every time the weight goes up, the mileage goes down. The line goes from top left down to the bottom right. It has the same idea as Prithvi, but it shows a negative relationship. Let's do the math. Finding M and C. We are using the same step, but with just a bigger number. Our what x we got is 8,300 and our sum of y is 117. In the step 1 we find the slope m which is a negative 0.0108, which is correct. It proves that the weight goes up, the mileage goes down. In the step 3, we find the intercept c, which is 229.54. So our final equation will be y is equal to negative 0.0108 x plus 29.54. We use the same formula as a Prithvi, but goes the opposite result. Now let's predict the mileage of new car. Here is our line on the graph. Let's guess the mileage for 1200 kilogram car. Okay. We follow the dash line up and across it, we hit about up to 16.58. We can check this by putting 1200 into our equation and match it. Does this make sense? Yes. Our data. Suppose a 1100 kilo car gets 17 and 1300 kilo car gets 15. Our guess of 16.58 is right in the middle. Our R square is 0.98, which means it explains that 98% of the mileage has been changed. That is a great score for just one variable. How accurate is our data? Can we trust the model? The residual plot tells us how far of our guess was for each point. See how the dots are scattered randomly around the zeros. This is the pattern. The random scatter is exactly what we want. It means our linear model is working. Simply, for simplification, just put 100 kilos added to the car. The mileage drops by 1.08. Remember this only works for the cars which is 800 to 1700, which is in our table. Okay, you have to know the limit of your model. Okay, verifying the result. We did the match by the hand. Now let's try with the computer. This is a C++ code for our car weight and the mileage data. At the top, you can see the 7 data written in 2 arrays. Just before the loop quickly adds up all our total with a no match mistake. The code then uses a normal equation to find the slope and intercept. But I want you to notice the bottom part of the code. This is where the actual calculation of the residual for every single point. If you look at the terminal output on the right, it is it's perfectly matched for our manual work. Okay, the slope is negative, which is 0.0108, and intercept is 29.54. And the gas is for 1200 kilo car is exactly 16.58. Below that, you can see that exact residual for all 7 cars. Every single one of those numbers matches the dot of the residual plot we just looked at.
So that's our presentation, and let me leave you with one thread that ran through everything of our presentation. Riola gave you the tool, partial differentiation, the ability to isolate one variable's effect while keeping everything else still was done by Sogantika using linear regression, minimizing the error, producing the normal equations, and the cost function, etc. And Prithvi applied it to a salary data and predicted a number that wasn't in the dataset. Vivek did the same, but for the fuel efficiency of a car and got it right to 2 decimal places. One concept, 2 completely different datasets, 2 completely different stories, and same mathematics throughout, partial differentiation and linear regression. That is the power of computational mathematics. It doesn't care what you're predicting, it just finds the truth in the data. Thank you for listening, and we are Group 9.